Welcome to the next lecture in the series on condensed matter theory. In this video I want to derive the linear response of a system, its susceptibility, in the time domain. And actually we'll be able to derive not only the linear but also the higher order response functions. And for that we start with a time-dependent Hamiltonian, which is given by a time-independent Hamiltonian and a small perturbation, in which we will make an expansion, which is the time-dependent Hamiltonian. Now, what we have seen in the previous video, first by an example and then generalizing that example, is that in principle we can make a Fourier transform of our time-dependent perturbation, H1 of t e to the I omega t dt. Then we get our Hamiltonian in the frequency domain, so prefactors times sine omega t, or e to the I omega t. And with that we can use the susceptibility in the frequency domain and solve the entire problem. The nice thing is that susceptibility in the frequency domain, the response is a product of the susceptibility times the driving force, whereas in the time domain it's a convolution. But what I want to do in this video is derive directly in the time domain what happens to our system. So in the time domain, we want to answer the question, what is our wave function? When we know that at time equals 0, the state is in psi 0, then what is psi t? Now, if our Hamiltonian was time independent, we would be very simple, able to answer this, because then we know that we have a time evolution operator, e to the I h t divided by h bar times psi 0. That is for time independent Hamiltonians. But now our Hamiltonian is time dependent. Of course, at time t, we know what the Hamiltonian is. So for an infinitesimal time, we can still use this exponential and say this is e to the I h t delta t of phi t. Such that if we take an infinite of such infinitesimal time steps, we have that psi t is the limit of our number of time steps to infinite, and then a product e to the minus I divided by h bar, h at t prime, delta t prime, phi 0, whereby delta t prime is 1 over n times the total time that we want to evolve, and t prime is given by j times delta t prime, and we are summing over j1 to n. Now, for an Hamiltonian that commutes, we can easily write the product of two exponentials as the exponential of the sum of the two. E to the power x times e to the power y is e to the power x plus y. But we have the problem that our Hamiltonian at two different times not necessarily commutes. So when this is non-zero, then we have to be a bit more careful, but we can still sum up our exponential or multiply our exponential at two different times, if we take into account that in our product we have the larger times, the later times always to the left of the earlier times. So now we include the time order operator, e to the minus e to the I h t plus delta t plus h t delta t, where the time order operator states that when you write this exponential as a sum of polynomials, then you have to move the Hamiltonian at a later time to the left of the operators at an earlier time. With this notation, we can rewrite our product as the limit of n goes to infinite, and then the time order operator e to the minus I over h bar. And now instead of a product of exponentials, we can sum inside the exponential. J is 1 to n h at t prime delta t prime, where t prime and delta t prime are just given by the time steps psi 0. We can now change the sum to an integral, and this is t, the time order operator, e to the minus I over h bar, and the integral from 0 to t h t prime dt prime, acting on psi 0. Now that's all nice and well. What we want to do is look at the evolution in terms of orders of h1. So we want to expand this in orders of h1. So we're going to write h as a sum of h0 and h1. And for that we'll actually go back to the definition of the time evolution as we had before. But first of all, we want to write a Taylor series in terms of delta t prime, because we can neglect all orders higher than the linear order in t prime, as we will take the limit of delta t prime to 0. So we find that psi of t is the limit of n to infinite, pi j is 1 to n, 1 minus I over h bar, h t prime delta t prime, plus things quadratic or higher orders in delta t prime, and they will all go to 0 as delta t goes to 0. Now let's substitute h for h0 plus h1, and then we'll find that this is the product of 1 minus I over h bar h0 delta t prime minus I over h bar h1 at t prime delta t prime, acting on phi 0. And this is still exact because indeed this goes exactly to 0. Now we're going to regroup our product in different orders of h1. We can act once with h1 or 2 times or 3 times, depending on if you in your product only multiply those or multiply h1 1, 2 or 3 times in there. So to 0th order in h1, we have the limit of n to infinite, pi j is 1 to n, 1 minus I over h bar h0 dt prime, acting on phi 0. So this is our 0th order. We can now look at the linear order in h1. Again, we have a limit of n to infinite. H1 can act at different times, so we have to sum. N is 1 to n, because for each of them we have a possibility to act with h1 one time. And then we have a product, j is n plus 1 to n, which is the propagation with h0 after you interacted with h1. Then we have the term where we interacted with h1. And then we have the product of j is 1 to n minus 1, 1 minus I h bar h0 dt prime acting on psi 0. So that's the first order. And then of course you can act 2 times with h1, 3 times, etc. to get the second, third, fourth order. Now the products where we only have h0, we can resum again, and that becomes an exponential, such that our wave function at time t is given by the propagation by h0 of psi 0, and then we have here minus I over h bar, and then the integral from 0 to t, because we have the different times at which h1 is interacting with our system, e to the minus I over h bar, h0 t minus t1, h1 at t1, and t1 is running from 0 to t, e to the minus I over h bar, h0 dt1, dt1, phi 0. Now we can also have a look at the second order, where we have 2 interactions in h1, so this is minus I over h bar squared is minus 1 over h bar squared, integral from 0 to t, integral from 0 to t2, where we have a propagator, I h bar, h acting at t minus t2, an interaction at the time t2, e to the minus I over h bar, t2 minus t1, h interacting at the time t1, e to the minus I over h bar h0 t1, and then the t1, the t2, psi 0, plus the higher order terms. In terms of diagrams, a state can propagate from t is 0 to t is t for a full Hamiltonian given by h0 and h1, and h1 is time dependent, and that propagation is given by the Baire propagator given by h0 plus the propagation of the state from 0 to t1. Then we have an interaction with h1 at that time, and then you propagate from t1 to t plus the propagation from 0 to t1. You have the interaction, the propagation from t1 to t2, you have another interaction, and the propagation from t2 to t plus etc, etc. You can have 0, 1, 2, up to infinite interactions in your propagation at different times. And here we assume that we have implicit integration over all intermediate time steps, where t1 can be between 0 and t, and t1 here can be between 0 and t2, and t2 can go from t1 up to t. And that means t2 can go from 0 to t, because t1 can be 0. So with this, we now can calculate the expectation value and with the response. So if we look at our wave function and now calculate the expectation value of operator O, then this is given by phi 0 and then for the first term this is just e to the I over h bar h0t O e to the minus I over h bar h0t psi 0, so that's the 0th order susceptibility. And then the linear susceptibility would be phi 0. And now I want to be linear in h1, so I either take the linear part in h1 for the wave function multiplied with a 0, or I have the zeroth order at the bra and the first order at the ket side. So let's first take the zeroth order on the bra side. H0 O, and then we have the first order propagation in the wave function. H0 t minus t1, h1 at t1 e to the minus I over h bar, h0 t1 dt1 phi 0. And then of course we can also have the interaction on the ket side or on the bra side instead of the ket side. And then we have the complex conjugate, so we have here the plus IO per h bar integral from 0 to t e to the I over h bar h0 t1 h1 at t1 e to the I over h bar h0 t minus t1 dt1 O e to the minus I over h bar h0 t psi 0. So the zeroth order of the wave function on the bra and the ket side, the first order of the wave function on the ket or the bra side. And of course you have the higher order. Now let's write our operators in the interaction picture. So O h of t is in the interaction picture I over h bar h0 t O e to the minus I over h bar h0 t. And you have to be a bit careful because I have time independent operators and time dependent operators. So I'll separate that by putting the Heisenberg h before or after the time is e to the I over h bar h0 t h1 at t e to the minus I over h bar h0 t, where h1 of t is an operator that already depended on time, even in the Schrödinger picture. And now in the interaction picture we have the h and either before the t for a time independent operator or after the t for a time dependent operator. But with this notation we can write for the expectation value of O at time t that this is psi 0, the operator O in the interaction picture, plus I over h bar, the integral from 0 to t. And we here see that we have if we take the h0t to the left, then we have here O in the interaction picture, and here we have h1 in the interacting picture at time t1. So this is psi 0, and we have OH or HO minus OH. So that gives you the commutator between h1 at time t1 in the interaction picture with OH at time t in the interaction picture of psi 0 dt1 plus O h1t squared. So the zeroth order and the first order response of your system. Now in order to calculate the susceptibility, we have to assume that our time dependence is given by a time independent operator times a time dependent function. So as a function you only scale your operator, you don't change internal structures. And then we can define a susceptibility. Because in this case this is given by the zeroth order plus I over h bar integral from 0 to t psi 0, and now we can take here h1h of t1. So this is the time-independent operator in the interaction picture commuting with the time-independent operator t in the interaction picture. Psi 0 d, the t shouldn't be here, times our function f of t1 d t1. And this is a convolution such that we can write our linear susceptibility in the time domain at time t, depending on t and t1, is, and let me put in a few theta functions such that we can take the integral from minus infinite to infinite. So we have theta t1, theta t minus t1, I over h bar, psi 0, h1, h, t1, oh, t, psi 0. In general, both t and t1 are important for your susceptibility. If your wave function is not an eigenstate of h0, then the propagation with h0 will induce some non-trivial dynamics, and then it matters at which point in time you make a perturbation to it and then do a measurement. Now, when psi 0 is an eigenstate of h0, then the dynamics that you get on the bra and the ket side just will be a phase and they will cancel each other. Such at that point it doesn't matter anymore at which time you do your experiment. So if h0 psi 0 is e0 psi 0, at that point only t minus t1 is important. Then it doesn't matter anymore when you make your perturbation. You make a perturbation and only the time after that perturbation, when you do your measurement, is important for the outcome of that measurement. Whereas when you're not in an eigenstate, then it matters at which point in time you do your measurement, or you make your perturbation and then do the measurement. So in this case, we can define our susceptibility depending only on the single time, and this is theta t, because you better not have a response before you make the perturbation, and t now tells you what the time after the perturbation is when you do the measurement, psi 0, and then the commutator of the Hamiltonian that describes the perturbation that you make, and the operator that tells you which measurement you do. And that now is our linear susceptibility. Thank you very much for your attention. Hope to see you in the next video. Stay healthy.